Dr. J here with a guide to subsets and set comparisons. Before we get started, I have two announcements. The first is if you would like to be taking notes on printouts of the slides, there's a link in the description that you can click on to get a download printable version of the slides. The second announcement is that last time when we talked about sets, I neglected to mention a very important set called the empty set, and so I will be introducing that set here today. Now, getting started talking about set comparisons, there's an analogy to inequalities that you're familiar with from real numbers. So in particular, these kind of inequalities. 1 is less than 2, 100 is greater than 99, pi is greater than or equal to pi. Here is one with a variable. 5.5 is less than or equal to the variable x is less than 23. Now, using the notation we have last time, there's another way that we can write this set. So we can write this set as x is in the half open interval 5.5 to 23, where that half open interval includes the endpoint 5.5. This arrow symbol that was sort of the double lines and the arrow on the end, that arrow symbol represents implies. So the statement on the left here implies the statement on the right. All right, so you also should be familiar with some inequality rules. So here's an example. X is less than y implies that x is less than or equal to y. Here's another one. X is less than y implies that y is greater than x. But it also is true that y being greater than x implies that x is less than y. And so here we have that similar arrow symbol, but now it goes in both directions. And so this is typically referred to if and only if. So x is less than y if and only if y is greater than x. We have sometimes relationships we can draw from multiple inequalities. So x is less than or equal to y is less than or equal to z. That implies that x is less than or equal to z. If we have the same kind of relationship, but without one of the equalities, say x is less than y is less than or equal to z, that implies that x is less than z. All right, so that's inequalities, and there's a relationship between the set comparisons that we're going to be doing and the subset definition and superset definitions that we'll get to that relate to these inequalities. But before we get there, I want to introduce this empty set. So the empty set, as you can see here, the brackets, the curly braces, have nothing in between them. And that indicates that there's no elements in this set, and that set is called the empty set. And the empty set is commonly denoted by a 0 with a slash through it. So the empty set is just a set with no elements in it. Now let's get back to our interest today of comparing sets. So here's a few sets, 4 sets, and we're interested in how do we compare these sets. So we have the empty set, we have the set that just has the two integers 1 and 2, we have the open interval 0, 1, and we have the natural numbers, where here I'm reminding you that for our purposes, the natural numbers will include 0. So now how do we compare these sets? And there's a number of ways we could do so. One is that we could think about how many elements are in the set. This is a topic called cardinality that we will actually be talking about in the future. And so we could compare those, but we'll leave that for now. We could talk about the values of the elements in the set and to see whether they are bigger or smaller than values in another set. So we might say, hey, that set 1, 2, right? Both of those values are bigger than any of the values in the open interval 0, 1. So that's another way we could compare sets. But the way we're going to compare sets today is to say, look, we have one set, and we might have another set that has all of those elements. For instance, the natural numbers include the integers 1 and 2, which is one of our sets, right? One of our sets has just the integers 1 and 2. And so somehow there's a relationship between those two sets because the natural numbers already includes those numbers 1 and 2. And that's the notion that we're going to be getting at today with these set comparisons. And so in particular, what we're going to be doing is we're going to be comparing sets by asking these questions. Does one set, call it A, have all of the elements that another set has, call that set B? So does set A have all of the elements that set B has? Just like in our natural numbers, the natural numbers there have all the elements that the set that includes just the numbers 1 and 2 has. Now, if it does that first set have at least one more element than the second? So in this case, the natural numbers, in fact, have lots of more numbers than the set that just includes numbers 1 and 2. And so that's the idea we're going to be getting at today when we talk about supersets and subsets. So let's get to the definition of subset. So a set B is a subset of a set A if every element of B is an element of A. And if B is a subset of A, then we write B with this C symbol and the equal sign, the partial, equal sign underneath. So B is a subset of A. That part equality line underneath just indicates that it can be the case that these two sets are in fact equal. Just like when we have our greater than or less than or equal to signs. All right, so sometimes we want to make sure that a set is actually smaller than another set, right? Just in the way that with inequalities, we want to make sure that a number is less than another number and not just less than or equal to it. And in this case, we're going to call that a proper subset. So B is a proper subset of A if B is a subset of A, for one, and there's at least one element in A that is not in B. If B is a proper subset of A, then we write B with just that C symbol, A. Okay, so here's a couple of examples. So the set that includes integers 4 and 5, that is a subset of the set 3, 4, 5. But it also is a proper subset of that set. So 4, 5 is a proper subset of the set 3, 4, 5. Because the second set has that 3, which the first set did not have. Thinking about our important sets from last week, we have that the natural numbers are a proper subset of all the integers. In particular, the natural numbers do not include the negative integers. We also have that the integers are a proper subset of all the real numbers. Right? There are lots of numbers that are not natural, like 1.5 or pi. We also have that the empty set is a subset of any other set. And this is true even if you talk about sets that are not just numbers. Okay? And we had to keep the equality there because we could have chosen A to be the empty set, in which case those two sets would be equal. All right, so we have the reverse idea, right? Just like with inequalities, we have the less than, and there's the opposite version, that's the greater than. So here with comparing sets, we have subsets, and then we have supersets. So A is a superset of B if every element of B is an element of A. And if it is, then we write A is a superset of B. Again, at this point, we're allowing equality to occur. If we want to eliminate the chance of equality, then we call it a proper superset. So A is a proper superset of B if A is a superset of B, and if A has at least one element that is not in B. If it is a proper superset, then we write A, we've turned that C around now, is a proper superset of B. So some examples, right? So the set 3, 4, 5 is a superset of the set 4, 5, but it's also a proper superset because of that number 3. We have the natural numbers here are a superset, a proper superset of this set that includes integers 0 up to 533. Here we have that the real numbers are a superset of the interval -infinity to infinity. And if you remember from last time, that was actually our definition of the real numbers. And therefore, the equality actually exists here, or occurs here. All right, so just like with the inequality symbols, if we want to, we can negate them by putting a slash through the symbol. Right? Just like we might do with an equal sign, we put a slash through it, which you could also do with the inequalities. So here we could have a not superset, not subset, not proper subset, not superset, not proper superset. All of those are possibilities. Here's a couple of examples. So the set 1, 1.5, and 2 is not a subset of the natural numbers. It also is true, though, that the natural numbers are not a subset of the set 1, 1.5, and 2. And now this brings up an important point when using these not versions of the symbols. In particular, you need to be a bit cautious here that some of the inequality rules that you might want to translate into set comparison rules don't always hold. Right? In particular, don't hold for those symbols that use the not those set comparisons that use the negated version with a slash through it. So here's a simple example. So if we have two real numbers, call them a and b, and we know that a is not less than b, well, that implies that a is greater than or equal to b. And so we might want this same kind of relationship to occur for sets. So we might want something like this. Let's say that a is not a proper subset of b, and we want this to imply that a must be a superset of b. But it turns out that relationship is not the case. And you can tell it's not the case with a simple counterexample. So here's one version. Here we have the set that has the integers 1 and 2, and it's not a subset of the set that has the integers 1 and 3. And but it's not true that the set 1, 2 is a superset of the set 1, 3. Right? And so that's just an example where that relationship does not hold. Okay, so the main point here is if you're using the negated versions of these set comparisons, you need to be a bit careful about what rules apply. All right, so we do have rules that apply here, just like we would have rules for the inequalities. And so what you might want to do on your own to make sure that you understand these subsets and supersets is to make sure that these rules make sense to you by just intuitively working through them. So here's an example. So A is a proper subset of B, implies that A is a subset of B. Well, number one, that's true by definition, right? But even if you try to take the definition, you said, okay, so if A is a proper subset of B, that means that all of the elements in A are in B. But there's also some element in B that's not in A. Okay? And this implies that it's a subset, that A is a subset of B. Well, we knew from the definition of a proper subset that in fact all the elements in A are in B, and therefore A is a subset of B. Similarly, you can go with the reverse direction. You can do a series of set comparisons, right? And these are the kind where you should sit down and verify these rules to yourself and make sure that they make sense. By the definition of subset and superset, we know that if A is a subset of B, that implies that, well, that's true if and only if B is a superset of A. And similarly with, I guess I said the non-proper version, this right here should have been the proper version. Here's now the version with the possible equality. As a summary today, we talked about subsets and set comparisons, and in particular we asked these two questions. Does a set A have all of the elements of a set B? And if yes, does set A have at least one more element than set B? We introduced the definition of these terms, subset, proper subset, superset, and proper superset, and we introduced a number of rules relating to these set comparisons. Next time we will be talking about set operations. So just like we have operations of addition, subtraction, multiplication, division, and so forth with numbers, we have operations with sets, and they are called union, intersection, and complement. Until then, have a great one.